Hey there, AP Physics students. Today is October 27th, 2011. It's Thursday, and this is what you're going to be doing today. First, you're going to be taking a Unit 3 homework quiz. Now, this homework quiz is on its own paper, so you don't need to use your own paper. You're going to take the quiz on that paper itself. So in a few minutes, I'd like you to pause the video and then take the homework quiz, and it should take about 20 minutes. So after about 20-25 minutes, if the substitute teacher would please collect the homework quiz when everybody's done, and then we'll start assignment 5, which is right here. I'd like you to read from chapter 9, section 3. This is all about collisions in one dimension, and do the example problems, questions, and problems that are listed here. And then you'll have the rest of the class period to do problemathon. You can work on the take-home test, work on any of these assignments. Whatever you need to do, get it done. Okay, so what I'd like you to do right now, please pause the video. Just hit the enter button and pause it. Take the homework quiz, and then when you're finished with the homework quiz, go ahead and start the video once again by hitting enter. Okay, go. All right, today let's do assignment 5. And to do assignment 5, I'd like to review momentum with you and talk about what impulse is. That's what we did last time. Then today we're going to talk about collisions in one dimension. Now what we mean by one dimensions is collisions that are along a straight line. Okay, we'll talk about two-dimensional collisions next time, but all of these collisions are along a straight line. Now there are two kinds of collisions we're going to talk about: elastic collisions and inelastic collisions. And inelastic collision has two types: just inelastic collisions and then what we call perfectly inelastic collisions. So we'll talk about that. So let's get started. Let's review. First of all, let's talk about momentum. We said that momentum is really just the mass of an object times its velocity. So we'll use the letter lowercase p to represent momentum, and we say it's equal to m times v. So that's our definition. This really defines momentum. And then good old Sir Isaac Newton, he said, hey, take the derivative of this, and you get what he called his second law. In other words, a net force is really the derivative of momentum. Now, let's show once again that this is what we were dealing with before. We said that momentum is defined to be m times v. If you assume that the mass is constant, that comes out of the derivative. So this becomes m dv dt. And of course, dv dt is acceleration. And so we get the equation, the net force is equal to ma, which is what we had before, but now that net force can be thought of as the rate at which momentum changes for an object due to a net outside force. Okay. All right. Now we took this expression for the net force and we rearranged it a little bit to define what impulse is. If I say a tiny change in momentum is equal to that net force times a tiny change in time. And then we just take this and we integrate it over some interval of time, some t initial to t final. And this gives us the impulse momentum theorem that says the change in momentum of an object is due to an impulse. And an impulse is the integral of force over time. If the force is constant, and we're going to be dealing with a lot of problems where the force is constant, then you can say the change in momentum is just equal times the net force times the change in time. So this is the, and this was called impulse right here. And the result of that impulse is a change in momentum. And this is a law of nature. This describes nature very, very nicely. Everything we observe about nature, you know, when forces are applied over time, this works. This really does work every time we observe it. So now what we're going to do is we're going to apply this to a situation that many of you have experienced in life, maybe out there in the parking lot even, and those are collisions. So let's talk about collisions. Now we're going to kind of restrict this to keep it simple. We're going to talk about two objects that are colliding, and what a collision is in physics is two particles come together, interact with some force, and then fly apart. Okay, that's a collision. And it can be two cars hitting, two billiard balls smacking into each other. It can be two galaxies colliding with each other, but they never actually hit each other. It's a gravitational collision. So, you know, and they're applying forces to each other. It can be atoms smashing into each other with using the electric force. So collisions are something very common in nature and very useful, and it's a good thing to understand. So let's get going on collisions. Imagine a ball of mass m1, and let's suppose it's moving along a straight line like this. So this is a velocity vector here. And then we have another ball. Maybe it's a little bigger, m2, and maybe we can have it moving like this towards, they're moving together. So when they come together, they're going to collide. Now I'm going to get rid of these velocity vectors here. Let's take a look at the instant of collision. Well, it's not really instant. It takes time for them to completely interact. Now they're touching each other here. So here's M1 and M2. Now they hit each other. They smack into each other. So this ball right here is going to apply a force here, isn't it? And this is going to be the force of ball 1 on 2. But we know from Newton's third law that for every force on one object, that is object 2, there's an equal and opposite force on the other object. So this is going to be, whoops, this is the force, I'll put it up here, the force of object 2 on 1. So this is the force of 1 on 2, 2 on 1, and they are equal and opposites. Now, let me back up a little bit here so you can see this little ridiculous demonstration I'm going to do. When two things hit each other, okay, it takes time for them to hit each other. So I'm going to imagine my two fists are going to come together and they're going to hit each other. And when they do, they go bam, like that. Or actually, bam. Okay, that was real time. Bam. But in slow motion, you would go bam, and then they fly apart. Now, my fingers pointing represents the force. So there's the equal and opposite forces. But when I'm saying bam, I'm really representing there the time interval, the delta t, that those forces are being applied. And one obvious thing from looking at this is that the force, is that the time that this force is applied is identically the same as the time that this force is being applied. The times are the same. They're identically the same. Well, here's what I know. I know that the force of 2 on 1 is equal, but in the opposite direction, to the force of 1 on 2, right? But they are happening for the same amount of time, delta t. So let's multiply these forces by the amount of time the forces are being applied to each ball. So this is going to be F(T1) times delta T equals F(1)(2). Oop, need that negative there. Times delta T. Okay? Zoom back in. Okay. So this is true, but what is the, and these are net forces. Let's say this is an isolated system, so there are no outside forces acting on these objects. These are the only forces acting. And so if you look at the force of ball 2 on ball 1 times time, this is the impulse on ball 1. And the impulse momentum theorem says that the impulse is equal to the change in momentum. So this really represents the change in momentum of ball 1. But that's going to be equal, but in the opposite direction, to the change in momentum on ball 2. Well, what does this mean? Well, let's add this. Let's put everything on one side. So delta P1 plus delta P2 equals 0. This is profound. This means that, hey, look, the change in when I add the changes in momentum, I get 0. The change in momentum on ball 1 plus the change in momentum of ball 2, you add them up, you get 0. Which means I didn't change the momentum of my overall system. If I look at my overall system right here, even after they collided, they're going to have the same amount of momentum in the system. Yes, this ball gets its momentum changed. And yes, this ball gets its momentum changed. But the changes are equal and opposite. So when you add up those changes, you get 0. This means that the total momentum you had in your system before the collision is equal to the total momentum you have in your system after the collision. In other words, P initial equals P final. And if you have an isolated system where collisions are happening, this is true. There are no exceptions to this. This is a law of nature. And you can use this law to solve lots of problems. This is your basic equation you start with. And so what you would do if you had a collision problem, you have two objects like this, and these are their velocities before the collision. I would start, use given, find, and solve, but then I would say, okay, what's the initial momentum in the system? Well, there's only two objects in my system, M1, V1 initial plus M2, V2 initial. Well, that has to be equal to M1, V1 final plus M2, V2 final. This has to be true. This is always true for collisions problems. And this is the basic equation. Yes, when you solve problems, I want you to write this down, but this is how you're going to expand it for a two-particle collision. And virtually all the problems we're going to do in here are going to be two-particle collisions. And this is the equation where you start. And look at it. If you know the masses, you know the initial velocities, maybe you know one of the final velocities. I mean, you have to be given enough stuff to solve the problem. Then you can solve for whatever unknown there is. Okay, so that's it for part 1. We've talked about now collisions. Well, we reviewed momentum and impulse. Now we're going to, we talked about collisions in one dimension. In the next video, we're going to talk about the difference between elastic collisions and inelastic collisions, and we'll define what a perfectly inelastic collision is. So if you feel up to it, go ahead and start the next video.